So we are done with properties of matter. But if you have any doubts and questions remaining, especially because you have a test coming up, so we can spend some time on doubts and discussions in properties of matter before we move on to the next section, which will be simple harmonic motion, very important chapter for us. So if anybody has any doubts from the module or from HC Verma in properties of matter, then please just let me know or send me a text message in the chat. We'll discuss that first. Okay. Yeah. Okay, fine. So you have a doubt session tomorrow. I think you'll be able to cover that. And Vineet, I think I have sent the recording and the notes of the last session. The recording is from my cloud. It's not there on the YouTube channel for some reason, but I have sent the link to my Zoom cloud recording link along with the notes. The last lecture we had was on 24th. Okay, so in case you're not able to find it, just send me a message, Vineet, on WhatsApp. I will forward it to you personally. Okay. So let's do one thing. Let's move ahead with this thing with properties. With simple harmonic motion. Okay. And if anybody has any doubts, you can keep them ready, and perhaps towards the end of the lecture, I will ask again once if you want to discuss anything. So now we are coming to a very important and also like heavy in terms of weightage. Just Nikita, you have some doubts. Okay, let's discuss. At least some of these doubts we can discuss. Okay. So exercise 1, question number 6 and 17. So I'm just putting it up on the board, just a second. Okay, so question number 17, let's start with this. I'll go back to question 6. Exercise 1 in your module, question number 17. So uniform capillary of inner radius is held vertically such that one end is dipped in water and the length 1 centimeter is outside. Okay. So in this, actually, you have to use the standard values of surface tension of water, okay, which must be there in the module somewhere before. That's why it's not given here. And also the standard contact angle between water and glass. Okay. Again, it's not mentioned that it's a glass capillary, but the standard contact angle between glass and water is nearly 0. So from that, you calculate the normal capillary height and it is 2t cos theta upon density into radius into g. So radius, the value is given, and g you will use the standard value, and r is density is 1000 kg per meter cube. So you'll see that this capillary height that you will get, Nikita, it will come out to be more than 1 centimeter. You just look up the value of surface tension of water. It is, I think, something around 140 millinewtons per meter or something like that. Okay. So you will get the height definitely to be more than 1 centimeter, which means that what will happen? Water will not be overflowing because you already inserted it, but the angle will change. The contact angle will change. It will not be a flat surface. So overflowing will not be the case. It will not be continuously overflowing. Okay. Uh, it will not be perfectly flat also because there will be some contact angle, but the contact angle will become greater than zero. Okay. Rise the full exposed length, and the radius of the meniscus will be equal to the radius of the capillary. This will not be true because for that the contact angle should be zero. Okay. Yeah. Now we can calculate how much the radius of the meniscus will be, because whatever the radius of the meniscus, actually you can do this calculation directly since radius of meniscus is given to you. So if this meniscus is having a radius small r, then you can see that the amount of capillary rise that happens, that is the pressure difference to balance that. So rho gh has to be equal to 2 times surface tension upon that radius of curvature. So when you take the standard value of surface tension of water and density of water, you'll see you'll get the radius of curvature to be definitely greater than 1 millimeter. Most probably you'll get it somewhere around this. So I'm guessing this should be the correct answer. Is the question clear, Nikita? How to work this out? Okay, I'm assuming this is clear, beta. Please let me know if there's anything further to discuss. Let's go to question number 6 now. Kevin, I'm coming to your questions also after this. Yeah. Okay, so question 6 here. Okay, good. Okay, so question 6, large drop of oil floats through a column of another liquid. So this is that case where, you know, that oil drop inside that other liquid. So let's say this is our oil drop and the other liquid is, now what is happening? The buoyancy applied by the other liquid is greater than the weight of the oil drop. So initially it accelerates upwards, but as it accelerates, viscous force builds up and it develops a terminal velocity. So here the terminal velocity condition will be, terminal velocity will be in the upward direction such that the viscous force balances the buoyant force minus the weight. Understood? Na? So 6 pi eta into R into V terminal should be equal to density of the other fluid. Okay. So let's take that as rho 2 minus density of this fluid, this oil. Let's take this as rho 1. Okay. Into 4 by 3 pi r cube into G. Okay. And okay, so you don't even have to do the calculation. Velocity depends on what? So you can see it depends on the okay, it depends on the, now this coefficient of viscosity is for the pair of liquids now. So that itself depends on the individual viscosity of this liquid and this liquid. So here the coefficient of viscosity that we've written, this is not n naught actually, this is just n of liquids. That is oil was what theta itself depends on the coefficient of viscosity for coefficient for the other liquid. Okay, so that's why it depends on both of these, and it depends on the radius also. But that is also clear, Nikita. Okay, so it was just a bit of a conceptual question. Good. Okay. Exercise 2, question number 4, and Kevin, you have question 2 and 7. Okay, so let's move on to question exercise 2. Start with question. Okay. So two wires are shown. They are made of same material, okay, and have radii RA and RB. Block between them has a mass M. When the force of mg by 3, when the force F is mg by 3, one of the wires break. Okay. Achha, so which one will break? That depends on which one has more stress. No? So the stress in the wire A will be how much? It will be equal to, now we are assuming that the wire's own mass is negligible. Okay. So it will be F plus mg divided by pi RA square. Whereas the stress on B will be just F upon pi RB square. So now the condition for A to break is that this stress is more than this. So if RA is equal to RB, then you can definitely see that. Okay, just a minute. Okay, so Kevin, this is clear. Now the first option, if RA is equal to RB, then definitely you can see that A is having more stress than B. So A will break before B. That's fine. If RA is less than RB, then also definitely A will break first because it will have more stress. But if RA is equal to 2 times RB, now you have to check because F is given to us as mg by 3 now. So you have to put that value and check. Okay. And the last option is not correct because length has nothing to do with the breakage, unless of course we are taking into account the density of the wires itself. In that case, length does have play a role because the stress will be highest at this point, at the top of A, because it will be the combined weight of the whole system plus F. So it does depend on the length and all that also. But here we are neglecting the weights of the two threads or wires or whatever. So Kevin, I think this question should be clear, or you have an issue with the answer key or something? Okay, it's clear. Okay, now let's move on to exercise 2. Nikita, you had a doubt in question number 2. Okay. 2, sorry, 4 and 7. Next two questions we'll see will be 4 and 7. Yes, metal wire of length L, area A, Young's modulus Y is stretched by a variable force F such that F is always slightly greater than the elastic force of resistance when the elongation is L. So what is the resistance force, the tension? It is AY by L into, AY by capital L in this case. The natural length is given to us as capital L into L. So this is a tension. So force is always slightly greater than. So it's almost equal to, but greater than tension. Okay. So when the elongation is L, the work done, okay, by F will be equal to the potential energy stored. So it's slightly greater. So you can just take it equal to. So work done by F will be equal to the potential energy stored. Okay. Or the work done against the tension. So you know that will be half AY by L into small L square. Now you can just relate this by, this is equivalent spring constant of AY by L, and the extension is equal to small L like this. So hopes Nikita, this question is clear now. Okay. So actually the correct statement here is that the potential energy stored is this much. Okay. But the work done will be slightly greater than. It's almost equal to, but slightly greater than, because F is slightly more than that. So what happens is that the rest of that work, like what is happening as the force is pulling it, because the force is greater than the tension, the wire will be in a state of motion. Part of the wire will be in a state of motion. So the work done by F will be equal to the potential energy stored plus a very small amount of kinetic energy. It will be slightly greater than this, because this term will be half AY by capital L square. This term will be almost zero, but slightly greater than zero, because part of the rod is going to be in motion because you're in the process of stretching it. So in my opinion here, the C option is 100% correct. No heat is produced, that's also correct, because there's no non-conservative force involved. But the work done by the force should be slightly greater than this. Okay. Because really depends on how we interpret the question actually. Okay. Let's move on to 7th question. Jenny, you have a doubt in option D of that question, the 4th one? You're just doing that question. Why no heat is dissipated? Achha. Okay, why no heat is dissipated is because there is no non-conservative force. F is an external force which is acting in a sort of conservative manner. Okay. Or at least there is no dissipated force. Assuming that the wire is acting like an elastic material, so the internal force is conservative. We are neglecting things like air is. Okay. All right, so coming back to 7th question. Yeah. So 7th question, capillary tube is dipped in a liquid. The liquid rises to a height h. The free liquid surface inside the tube is hemispherical in shape. So if it is hemispherical in shape, it's like this. That means the contact angle is zero basically. Okay. So small r is equal to capital R. That's the case. So our h will be 2t upon rho capital R. Contact angle is tending to zero. Now the tube is pushed down so that the height of the tube outside is less than h. So it's that case only. This height is h. Now if you push it in such that the height above the liquid itself is becoming less than h, what will happen is that the meniscus will change shape. Now the radius of curvature of the meniscus will become greater than r. The contact angle will become greater than zero, so that the new height h prime, whatever that is, it is 2t cos of this new angle divided by rho r. So we have done a numerical problem based on this in class, you remember. I set up the values such that the contact angle was changing from 53 degrees to 37 degrees, or vice versa. From 37 was a natural contact angle to 53 degrees. So that kind of continuously. It will not come out like a fountain. Fill the tube, but it will not be hemispherical. This will be the correct option. So obviously, if you push it down, initially some liquid will come out, that extra liquid will come out, but it will not completely ooze out. I mean, it will not continuously ooze out. So Kevin, this question is clear, I hope, because we had done a numerical problem also based on this. Remember that problem where the contact angle changed from 37 to 53 because we pushed. Okay, so that kind of situation only. Okay, so hope you are clear with the concept now of this. So we are done with exercise 2 doubts, I think. Now let's come to exercise 3. Oh, Amog, you have a doubt in exercise 2, question 1. Okay, let's come to that. Yeah, part A. Okay. So part A says that no, when it falls under its weight, what is happening? This whole thing is acceleration g. So the tension is zero everywhere. So there's no stress. Strain is equal to zero. It's only when it's suspended under its weight, because the whole rod is falling with an acceleration equal to g. So if you make a free body diagram of any section of the rod, the net force acting on it should be equal to the weight of that section. So there's no tension. I hope this is clear, Amol. Okay, now let's come to exercise 3, comprehension number 2. Okay, so let's go through this comprehension carefully first, all of us. The interaction between molecules is called cohesive force. Different molecules is called adhesive force. Both are attractive in the range of about this much. So net resultant force is zero inside. But near the surface, the molecules do not exist on one side, thus it gives rise to surface tension. Okay. As surface molecules like B, this one, okay, so this is all that concept of cohesive and adhesive forces interacting, and through that, the concept of contact angle and all that. So these are the different situations shown to you. So Kevin, any part of the paragraph which is not clear to you? So see over here, CR is the relative cohesive force because of the other liquid molecules. On a molecule at any point on the corner over here, A is the net adhesive force, okay, because of the wall of the container. So F is the vector sum of adhesive and cohesive force. Okay, so you can see that in a acute contact angle, this is how the net force looks like. In an obtuse contact angle, this is how it looks like. And in a perfectly right angled 90-degree contact angle, this is how the net force because of cohesive plus adhesive should look like. Okay, so hope the paragraph is clear. Yeah, Kevin, the paragraph is clear. All right, so now let's come to the questions. So liquid particle B, which is present in the vicinity of a liquid particle A, can exert a force on A only if the distance between this is of the order of Armstrong. So that is like directly from the paragraph. You can see that the distance should be less than equal to 10 raised power minus 10. Angstrom. Okay, so you can see that this fits in that category. Okay, the free surface energy stored in the surface is because of work done against the cohesive forces. Is negative of work done by internal cohesive forces or work done by external agent against the cohesive forces to create the surface. Okay, then concave meniscus, that is this one. This is a concave meniscus. It means that adhesive forces are dominating over cohesive forces. Okay. So A goes with 1. Angle of contact is 90 degrees. That's this case. Okay, so that goes with this. And pressure below the meniscus is more than it by 2T by R. So pressure is greater. So that means it's a convex meniscus. If the pressure at this point is greater than the pressure outside, that means it is a convex meniscus. So if it's a convex meniscus, it means that the contact angle is greater than 90 degrees. So its adhesion is, less than, cohesion is dominating over this. So C should go with 3. Okay, so Kevin, hope this part is clear. Okay. All right. So now we'll move on to the next question. So we'll just do a few more questions, and in another 10 minutes or so, I want to move on to simple harmonic motion. Okay, so Kevin, you have some more questions in the subjective, right? 11, 9. Okay. And okay. Ashka, you also have in the subjective. Okay, so we're moving on to the subjective exercise next. Achha, Naman, comprehensive 1. Okay, so let's go back to comprehension 1 for a moment. So this is that Poiseuille's equation derivation, what we were doing last time. It's just that derivation you'll see. You get that formula of viscous resistance. P is the pressure difference over here. Yeah, it's named also as Poiseuille's. So fifth part, force acting on the tube due to the liquid. Okay. Yeah, so force acting on the tube will be the surface area of the tube into the coefficient of viscosity into the magnitude of the velocity gradient at which point R equal to capital R. Okay. So surface area will be 2 pi capital R into L. Okay, and velocity we had just seen was like this, right? It was V naught into 1 minus R square by R square. So what is our velocity gradient? It is minus of 2 V naught R by R square, right? So the magnitude of velocity gradient at the point R equal to capital R is how much? It is minus 2 V naught by capital R. Magnitude is just V naught, 2 V naught. So substitute that. Okay. So this is 2 pi RL into eta into 2 V naught by capital R. So this should give you the force. Okay, so Naman, fifth question is clear, I hope. Oh, sorry, I did the fourth question. Okay, let's come to the. Oh no, I did the fifth question. It's fine. Yeah, did the correct one. So hope this is clear. Okay, good. Yes. So now we'll move on to the subjective exercise. Okay, so everybody's online, so let's just continue. Yeah, so we were last, I remember we were going to discuss subjective question number 2. Okay, unfortunately, I've lost all the text messages because I got locked out. So if you can please send me the questions from the subjective exercise, those who wanted to discuss. I will try to discuss a few more of the subjective questions before we start SHM. We'll start with this. So two wires, their diameters are same. One is made of steel and the other is made of brass, are loaded as shown. Unloaded length of the steel wire is this much and that of the brass wire. Young's modulus is given. Elongation of steel and okay. So for the steel wire, you can see the tension will be different, and for the brass wire, the tension will be different. For the steel wire, the tension will be 4 kg into G. 4 kg into G plus 6 kg into G. So 10 G. And for the brass wire, the tension will only be 6 G. So for the steel wire, the elongation will be stress upon Young's modulus into the natural length. And for the second one, it will again be stress upon the same, tension upon the same area, Young's modulus of brass into L. So using this formula, you should be able to calculate. Okay. Just have to understand that the tensions are different and the Young's moduli are different, as are the natural lengths. So these are also going to be L1 and L2. But what is common for them is the radius. That's the only thing which is common. The diameter of the wire, so the radius. Okay, so hope this question is clear. Okay, now I'm moving on to okay, I'll come back to exercise 4 also, Jenny and Aman. Let me just finish a few questions here. So fifth question. Next. Okay. So surface tension based question. U-shaped wire is dipped in a soap solution and removed. A thin soap film formed between the wire and the light slider supports a weight of this much, which includes the weight of the slider. The length of the slider. Okay. So basically, they're not given a diagram in the question. I think this is based on an actual IIT question where there was a diagram also given. Yeah. So in this question, the diagram is missing. Anyhow, so basically, what you're doing is you have like a U-shaped wire frame which has a slider support. So this is your wire frame, let's say. It's made of thin metallic wire. And then you have some kind of a support which can slide on this. So just imagine you have two rings and a small massless or is having slight amount of mass rod kind of this. So this is your support. And now you have created a film of solution here. And you just place it vertically like this under the action of gravity. So the surface tensional force acting on that wire is balancing the combined weight. But the surface tensional wire force will be 2 times surface tension into length, where L is this length. Why 2? Because the film is supported by 2 surfaces, one above and one below. Okay. So the soap film, it has 2 surfaces, 2 parallel surfaces. So on this support, okay, so that's it. So this Ft has to balance mg. So 2 times the surface tension which you have to calculate into 30 centimeters. This force in newtons has to be equal to 1.5 into 10 raised to minus 2. So from this you should be able to get. So Kevin, you tried this method or the question was not clear to you, or anyhow, hope it is clear now. Okay, now it's clear, no? Okay. I hope you people are able to unmute yourself and speak if required. Like I have kept it in the settings. You can unmute yourself. Okay. Yeah, Vinith, I'll come back to exercise 4. Aman has also asked the same question, question number 11. Just a couple of more questions from this 7th and 8th. Let's discuss. Okay, so this Millikan's oil drop experiment, for the moment you can leave it because we'll discuss it in detail in modern physics. But if you remember the experiment, oh sorry Kevin. Uh, should I take you back to the question? There the idea was simply that 2 times surface tension into length. That was the surface tensional force. That had to balance mg. Okay, this length was given 30 centimeters. Surface tension was asked, m was given to us, whatever. mg was given to us, this whole thing. And surface tension was asked. Okay, you remember the diagram, no? Okay. Okay. Now let's come to this Millikan oil drops experiment. Terminal speed of an uncharged drop is this much. Okay. So uncharged drop per terminal speed, how we calculate from the normal method only, that mg buoyant force and viscous force in terminal velocity condition is such that viscous force is equal to the apparent weight. So 6 pi eta into r into terminal velocity is density of the solid, or in this case, density of the oil drop minus density of air into 4 by 3 pi r cube into g. So this is the first situation. Okay. Viscosity of the liquid is given of air at the temperature as well. Oh, we have to neglect the buoyant force also. So this thing neglected. So that's it. That's all you have to do. It is uncharged, so there's no electrostatic force. Okay. So density of oil is given. This one will neglect density of air. That's why we are neglecting the buoyant force basically. And that's it. Okay, so Kevin, this should be clear. Just equate the weight of the oil drop with the viscous force. So terminal speed you'll find out, and that terminal, the viscous force at the terminal speed is nothing but the weight. Okay, so this is done. Now let's move on to 8th question. Tank with a square base is divided by a vertical partition in the middle. Bottom of the partition has a small hinge door of this much area. The tank is filled with water in one compartment and an acid of relative density on the other. Compute the force necessary to keep the door closed. Okay. So this actually is a misplaced question. This doesn't have any data about surface tension or viscosity, and we are not talking about any surface. It is just that the force due to pressure difference has to be balanced by some net force. Okay. So basically you have, like, let's say this is the wall which is going through the center of the tank. This is the tank otherwise. So on one side you have oil, one side you have water or whatever. And in that there is a, okay, so this hardly matters. Vertical partition, small hinge door of area. So let's say this is the hinge door. And compared to the height of the water column, we will take the size of the door as negligible. So compared to this height, the height of the door itself is negligible. So we'll take it as a uniform pressure. So on the door from either side, there is almost like a uniform pressure into area acting, because the door size is negligible compared to the total depth of water on one side and oil on the other side. So water is applying a force of density of water into G into H into area, and oil is applying a force from the other side of density of oil into G into H into area. So the difference of these two forces, sorry, this acid, okay, whatever. So density of acid. So the difference of these two forces, which will be uh, 0.7 is the difference in density in gram per cc into G into 4 meters into area 20 centimeters square. That should be. So unfortunately, this is nothing to do with properties of matter. This is a fluid mechanics question. In fact, a hydrostatics question. So hope this is also clear, Kevin. Okay. Then we had question number 9, right? Let's discuss this. So bubble of this much. Okay. The air is now compressed isothermally. Yeah, this is a good question. So I'll explain this question separately to you. Just give me a moment. This is so in this, what is happening is that we have like a cylindrical tank in which there is air, and inside that there is a soap bubble. Now, initially, the air is at atmospheric pressure. Okay. So the air inside the soap bubble is at a pressure of atmospheric pressure plus 4 times surface tension divided by R. Let's say the radius at this point of time is R1. Okay. Now clear now why it is 4T by R1 and not 2T by R1, because it is a bubble. So it's a film of, it's a spherical film. So there are two surfaces, two concave surfaces, so one after the other. Okay. So now what we are doing is we are going to pressurize the air isothermally. Okay. So the question says that the air in the cylinder is now compressed isothermally until the radius of the bubble is halved. Calculate the pressure in the cylinder given that the surface tension of the soap film is so much and the initial radius is given. Okay. So initial radius is given to us. Okay. Atmospheric pressure is given to us. Surface tension of soap solution is given to us. Now it is given to us that next what we do is the pressure of the air that is changed to P naught plus some delta T P isothermally. So that what happens that the radius of the soap bubble, that should become how much? It should become half. Is it? Yeah. So the radius of this one should become half. So this time let us say the pressure of the air inside the soap bubble, that is P2. So this P2 will be how much? It will be P naught plus delta P, that is the external pressure, plus 4T by R2. Okay. So that is one thing. Okay. And the other thing is that the air inside the soap bubble, that is undergoing what kind of process? It undergoes an isothermal compression. Okay. So P1 into 4 by 3 pi R1 cube should be equal to P2 into 4 by 3 pi R2 cube. So this will now tell us the relation. So P naught plus 4T by R1, that is my P1, into R1 cube should be equal to P2, which is P naught plus delta P plus 4T by R2 into R2. I just cancelled the 4 by 3 pi on both the sides. Okay. So you can see here Now wait. So now, so what we have to do? We have to find the delta P. I think how much it is increased by. So we just have to calculate that delta P from this. Okay, so you can see that when I bring this term here, it will become 8 times. And substitute R2 as also R1 by 2. So this delta P, the increase in pressure will become 8 minus 1, 7 P naught plus this will be 32 minus 8. So that's how much? 24 T by R1. This should be the increase in pressure. So the net will be, of course, this plus P1. Okay, so Kevin, hope this question is also clear. There's another interesting question of this type somewhere in the exercises I'm forgetting. There we had to relate it in terms of the change in surface area and the change in pressure. Anyhow, so the same concept there also had to be used, that the air inside the bubble is undergoing an isothermal process. So P1 V1 is equal to P2 V2. Okay, and P1 itself is the outside pressure plus 4T by R. And P2 is again the new outside pressure plus 4T by the new radius. Okay, so final question in exercise, the subjective exercise, 11th one. Oh yeah, this only. See, this question was the one I was telling you. But in this, we have to do conservation of number of moles actually. Okay. So two spherical soap bubbles coalesce. V is the constituent volume change of the contained air, and S is the change in surface area. Okay. So what will happen is that you have individual soap bubbles which are of radius R1, okay, pressure P1, pressure P2, radius R2. They coalesce to form a single bubble of radius R and pressure P. Okay. So the air, this air combined here, the number of moles is conserved. So P into 4 by 3 pi R cube has to be equal to P1 into 4 by 3 pi R1 cube plus P2 into 4 by 3 pi R2 cube. So this is the equation. Now in this you put P as atmospheric pressure plus 4T by R. Put P1 as atmospheric pressure plus 4T by R1 and put P2 as atmospheric pressure plus 4T by R2. Okay. So in this equation, P was atmospheric pressure. So I'll just replace it as P naught because I have taken it as P naught. Okay. And V is the change in volume. Okay. So V is the change in volume. So V is going to be actually 4 by 3 pi R cube minus R1 cube minus R2 cube. Final volume minus initial volume. So I should replace V with this in this equation. And S is the change in surface area. So S is equal to 4 pi R square minus R1 square minus R2 square. Okay. So you will see that when you put these values of pressure in this equation, you will get those kind of terms. You will get terms which involve R cube minus R1 cube minus R2 cube, which will relate with the change in volume V, capital V. And you will get terms which are related to R square minus R1 square minus R2 square, because there is this 4T by R into volume terms also. So those will be related with the change in surface tension. So Kevin, if you understood, can you try the rest of the maths part yourself in this, like, or otherwise I will work it out for you. The concept of the question clear? Like P1 V1 plus P2 V2 is equal to the final pressure into the new volume, because total number of moles is conserved and temperature remains constant throughout. Okay. And the other thing is you are using the formula of excess pressure. Is it okay, Kevin? Okay, now we'll look at some remaining questions in exercise 4. Oh, there were no questions in exercise 3. No? So we have done. Okay. So Vineet, you're also clear with this question 11. Vineet and Jenny, both of you asked the same question. Question 11 of exercise 4. Okay. So I'm not working out the full question. Hope you can try it out yourself. If you have difficulty with the equations, just let me know. Okay, so I think that covers all the doubts from this thing, right? Properties of matter. So we can maybe spend the rest of the time today with basic introduction to simple harmonic motion. So that next week we can straight away get on with the technical aspects of simple harmonic motion. So next chapter we will do now is, next section of physics will be oscillations and waves. So in this chapter, we will first be discussing about simple harmonic motion. And within the same chapter, we'll also be discussing about angular harmonic motion. So these are two specific types of oscillations. And we'll discuss how they are specific, in what way. Then we will study about damped oscillations, which incidentally is quite an interesting topic, but it is only in JEE mains. It is excluded from JEE advanced syllabus. Okay. Then we will come to the waves part, which will start with transverse mechanical waves. In this, basically, we'll be studying waves propagating through a stretched spring, like the waves in any stringed instrument, string musical instrument like that. And the final part of this section will be longitudinal mechanical waves. Where we'll be studying sound, basically. Okay. We will be doing light or as an electromagnetic wave at a later stage. So this section of waves only consists of mechanical waves. So this is like, in a sense, it's a final part of mechanics. So let's start with simple harmonic motion today. From now on, we'll just refer to it as SH. So I'll explain the definition and the meaning of the term simple harmonic motion. Actually, each of these words, simple and harmonic, has a specific meaning in this. Okay. But before that, what we'll understand is based on periodicity or how motion progresses with respect to time. Okay, based on what we can say the evolution of any system with respect to time, we can classify it in certain categories. Okay, so any motion, and the motion need not be like motion in the mechanical sense. Okay, it can be anything where there is change with respect to time. So it could be a thermodynamic system where the thermodynamic parameters or the state of a gas is changing with time. So that also constitutes motion. Or it could be a system of charges, okay, where the charge is changing with time because there is some kind of redistribution of charge happening and things like that. But yeah, typically, like we'll start with simple examples where we're talking about motion in the mechanical sense. So there's actually Newtonian mechanics and motion of particles or rigid bodies and all that. So thinking in context of that, any motion can be divided broadly in two categories based on whether they have a tendency to repeat themselves. So repetitive motion, so that is called periodic motion. So if a motion repeats itself with a definite time period, then we call it periodic. Whereas if it does not have any such, repetitiveness, or it does not have any order in which it repeats itself in a definite cycle, then it is called non-periodic motion. Now further, so obviously non-periodic is the most common, whereas periodic is a bit more specific. So only certain types of systems will show periodic motion. Okay. But further within periodic motion, we can divide systems into two categories: systems which are moving periodically such that they are actually oscillating. Whereas we can also see periodic motions which are non-oscillations. So this is where the definition starts to get a bit technical. We all understand what is periodicity. A periodic motion is a motion which repeats in cycles with a definite time period. So it can be orbital motion, it can be oscillation, it can be so many different things. But oscillations are also having definite time period. Non-oscillatory periodic motions also have definite time periods. So how is there difference between the two? So let's start with that. So can you give me an example of something which is periodic but not an oscillation? Like just in terms of everyday understanding of science. Just can you think of any common everyday occurrence where you see something which is periodic, definitely, but it's not an oscillation. We cannot classify it as an oscillation. Anyone? Because the moment we see the example,
traffic light,
sorry,
traffic light,
traffic light, yeah, to a certain extent you can say, yeah. So that is like a very artificial system, but yeah, if traffic lights are rotating in a periodic cycle, like if it's a definite time period, then definitely we can say it is non-oscillation. Okay, anything else? Anybody else? You can think of this like one example is the cyclical changing of traffic lights. So that's what about like an orbital motion? Is it an oscillation or is it a non-oscillation? Like I think you completed gravitation by now, right? So circular orbits, elliptical orbits, you might be familiar with all these things. Can we call them oscillations or are they non-oscillations?
Non-oscillations.
Non-oscillation. Yes. So the orbital motion is a non-oscillation. In fact, much easier than just general orbital motion is just the case of uniform circular motion. That also has a definite time period. Okay. Okay. Now, all of you know oscillations, for example. You know that any pendulum is an oscillation. Okay. A spring mass system typically oscillates with a definite time period. Okay. So what is the difference between this and this? They are both periodic with a definite time period. But how come some of them are classified as oscillations, whereas some of them we cannot classify as oscillations? Is it anything to do with like whether the motion is one dimensional or two dimensional, or is it something more technical than that? Okay, what about this example? If we have a ball which is bouncing continuously from a surface where it makes a perfectly elastic collision. What type of motion is this? Is it oscillation or is it non-oscillation periodic motion?
Oscillation.
Okay, can you tell me what is the difference between this and, for example, a vertical spring mass system? If I attach this particle to a spring and it's not colliding with any surface, but I just release it under its own weight. So initially this is at L and U is 0. So this will also come down to a certain distance, then go back, come down, go back. Okay. Now, is there a difference between this and this case? They're both periodic. Okay. Is there a difference between these two? So let me give you a hint. Is there a mean position? In the spring mass system, is there a mean position? There is no.
So
Mean
can you
position.
repeat, sir? Sorry, I was having network issue. Can you repeat?
Yeah, so I'm saying that two systems that I have put on the side over here. One is a vertical spring mass system. So block is attached to a spring. You've done these type of questions in work energy, for example. So if you just release the block from rest with the spring in natural length, what will happen? It will pick up kinetic energy as it accelerates. Then it will go past the equilibrium position because it's picked up kinetic energy. So it will start decelerating, and like that, it will keep going back and forth with a definite time period. So this is one example. And the other example is the ball bouncing continuously from a certain height from a horizontal surface with a perfectly elastic collision. So both of them are periodic motion, but do they both have mean position, or does only one of them have a mean position?
Only one has a mean position. The ball's mean position will continuously go down.
Yeah, the ball does not have a mean position. Now you'll realize at any point of time of its motion, there is some net force acting on it. Generally speaking, it is gravity. And then for that brief, millisecond or nanosecond or whatever it is in contact with the ground, there's a very strong amount of collision impulse acting on it, which is suddenly changing its momentum, right?
Yes, sir.
Yes. So there is generally speaking no stable equilibrium position. Whereas the spring mass system, there is a stable equilibrium position. No? Instead of releasing the block directly, if you gently lower it, and let it be at rest where it comes to equilibrium, what will happen? It will remain in equilibrium there at that point.
Yes.
And that is a stable equilibrium point, because if you take it above it, there is restorative force downwards. If you take it below it, the spring will dominate. So there is restorative force upwards. So it has a defined mean position. But the other one, the ball bouncing, it does not have a defined mean position. Now you think of all the other examples you've taken. Pendulum has a defined mean position. It has a stable equilibrium position. That's the lowest point of the pendulum.
Yes, sir.
Yes. Yes, sir.
And spring mass system obviously has stable equilibrium position. But none of the others, there is any point during the motion. This, whether we are talking about obviously the changing of traffic lights is a very abstract example. But orbital motion, uniform circular motion, the ball bouncing on the ground continuously, they don't have any mean position. Okay, they don't have restorative force. They don't have stable equilibrium position. So those are the necessary conditions to define the motion as oscillation. Not any periodic motion is an oscillation. A periodic motion is classified as an oscillation when it is more specific. It is a to and fro motion with respect to a mean position. And what is a mean position? It is nothing but a stable equilibrium position. So that means the system must have internal forces such that they are restorative in nature, and there is some point at which the net internal force is zero. So there is equilibrium. So there's an equilibrium point, and when we displace it from equilibrium, there is restoration. There are internal restorative forces. That means it's a stable equilibrium position. So an oscillation is a very technical definition. An oscillation is a specific type of periodic motion. It is a periodic to and fro. So again, this to and fro business is a bit like layman's language, but we'll make it more technical. So it's a periodic to and fro motion about a mean position. With definite, that means fixed value of amplitude and time period, both the things. Now, slightly more technical. So what is a mean position? It's a stable equilibrium position. And what causes the system to go to and fro about it is due to the action of the restorative forces. So wherever there's restorative force and there's an equilibrium position, the equilibrium position is a stable equilibrium position. Okay. So restorative forces are internal conservative forces that tend to restore the system, or that you can say point towards the equilibrium position. So therefore, the equilibrium becomes a stable equilibrium position. So the system must have this quality. It must have an equilibrium position defined, and it must have restorative force when you displace it from equilibrium. Then only it is capable of oscillating. Okay. So I'll just minimize this and leave you with time to go through this. I hope you've understood the difference between a non-oscillation and an oscillation. So this does not have a mean position or restorative forces. But overall, it has a definite time period. Okay, so next thing, so any system which is capable of oscillating, it will always have a potential energy graph, which is such that it shows a point of local minimum. It can be the global minima, it may not be the global minima, whatever. But in general, if the potential energy graph is something like this is the potential energy as a function of position or whatever, then you can see that all these positions where there's local minimum, let's say this is R equal to A, and this is R equal to B, these are all possible mean positions. Okay, so such a system can oscillate about any possible mean position. So the mean position in this case will be stable equilibrium, which is basically local minima of potential. So example, R equal to A, R equal to B. Now, for oscillation with definite amplitude and time period, there should be no dissipation of energy. So forces like friction or drag forces should not be there. Viscosity, these kind of forces should be negligible or absent. Otherwise, they become what we call damped oscillation. Over time, their periodicity changes and their amplitude also keeps diminishing. So there should be no dissipation of energy. So basically, there should be, for a perfect oscillation, there should be no non-conservative forces. So the only forces that are driving the system should be the conservative restorative forces. So the same thing if we want to analyze in terms of the force versus position. And by force here, it becomes an internal conservative force. So at the point A, you will see that the force diagram will look like this. It's minus del U by del R. So here the slope is positive. So the slope is negative. So the force will be positive. On the right hand side, similarly, you see that at the point B, again something like this only will be happening. So A and B are our stable equilibrium positions. Whereas this kind of point, let's say C over here, would be the other equilibrium point, but that would be unstable. This is unstable equilibrium because on the positive side there's positive force, on the negative side there's negative force, whereas A and B, they are stable equilibriums. Because on the potential energy graph they are local minimas. Because this is a local maximum, so it's an unstable equilibrium point. So any system that has internal forces which exhibit this kind of property, or any system which has conservation of energy with potential energy acting like this, is capable of oscillating. Yeah, Ansh, that is correct. Okay. The equilibrium position itself by definition means a position at which net force is zero. But restorative force is such that when we take our system away from equilibrium, the restorative force tends to take it back. So it is the type of forces that act naturally when we have a local minima of the potential energy graph. Okay. And Harpriya, I'll just answer your question. Yes, a lot of you had sent me answers which I had missed out. Revolution of the Earth, Jayani, that's correct, is another example of periodic motion but non-oscillation, as is the number of frames per second passing through a screen are huge. Hands of a clock, another example of periodic motion which is non-oscillating. So I'm just scrolling back for a moment. Yeah, third example was uniform circular motion. UCM, Harpriya, was the short form for uniform circular motion. Okay. So what we need in a system so that it can oscillate, we need that there should be some stable equilibrium position and there should be no non-conservative forces, so that the only force acting is the restorative forces. Or in other words, the potential energy graph should have a local minima point, which will be the mean position, and there should be no dissipation of energy, so that overall mechanical energy can remain conserved. That is as far as oscillation is concerned. Now we come to the main part of this next topic, which is simple harmonic motion.
To roll up 1 second.
Yeah. Now, simple harmonic motion further a special case of oscillation itself. It's a further classification, or you can say it is a subset of oscillations. So definitely it's a subset of periodic motion also.
Yes, done.
Okay, so hope these points are clear.
Yes,
Yeah, we need to explain stable and unstable equilibrium. Equilibrium in general is any point where net force is zero, but stable is where, okay, what happens is if you have your potential energy graph versus position, which you can write as R or X or whatever, and your potential energy graph has a local minimum. Okay, so now what is the internal conservative force? Remember, it was minus du by dr. So if I correspondingly plot for the force versus position, now you can see that at whatever position the potential energy is reaching a minima, at that position the force will be zero because the slope of this graph is zero. So the force is zero at this point. But at such a point, the slope is negative. So the force is what type? Positive. And at such a point, the slope is positive. So the force is negative. So that means if this is the body, if it is at R equal to A, the net force on it is zero. So its acceleration is equal to zero. But the moment I take it to A plus delta R, what happens? The force acting on it is negative. So you can see it has a tendency to come back. Okay. With the moment I take it to A minus delta R over here, the force on it is positive. So these are restorative forces. So because they are restorative, so this becomes a stable equilibrium position. Okay. So I won't write acceleration here unnecessarily to confuse you. So the net force here is zero. So that's the equilibrium position. So local minimum of potential energy is a stable equilibrium. But at the same time, if the potential energy graph is having a local maxima at some point of time or at some position, then again at that point the slope is zero. But unlike the previous one, when we look at the force, at the point B, the force will be zero. But when I take the graph to the left of B, the slope of this one is positive. So the force is negative. Okay. So you can see that force is negative at R equal to B minus delta. And the force is positive at R equal to B plus delta. And the force is zero at R equal to B. So this is an equilibrium position, but these are non-restorative forces. They take the system further away. So here on either side of the equilibrium, there is force acting in such a way that it takes the system further away from equilibrium. So these are examples of non-restorative forces. Very good example of this is if you have this kind of situation that on a smooth surface, now you got two fixed charges. So A and B are plus Q naught each, and they are fixed. And now you have a slidable block on which there is another charge. Okay. Now, if the charge of C is positive, then what will happen? Midpoint is the equilibrium position, but is it stable or unstable? So net force will be 0 here. Okay. But when I bring the charge particle here, C, what will happen? This one's repulsion will dominate over that one's repulsion. So the net force on it is in this direction. When I bring it here, the repulsion, because it's positively charged, okay, so the repulsion of A will dominate over the repulsion of B. So the net force will be like this. So further, this is what kind of equilibrium? Stable. But had it been negatively charged, if C were negatively charged, then midpoint would be unstable equilibrium. And you can show this very easily using the potential energy graph also. You can write the potential energy function of the system of charges in terms of x, the distance of C from either A or B. And you can see that when C is positive, it will show you this kind of a potential energy graph. For positive case of C, your potential energy versus the distance of C from one of the charges will be like this. Asymptotically approaching infinity, like this. Whereas for C being negative, the graph would be actually like this. The potential energy would be a negative quantity, approaching minus infinity at 0 or n. So this is unstable, this is stable. Okay, so hope with this concept of stable and unstable equilibrium is also clear. Okay. So these things are going to become important in this chapter. So maybe after you complete your test, you can do a bit of revision of work by energy. All these things that potential delta U is negative of F internal conservative dot ds, or the internal conservative force is negative gradient of potential energy. This relation, or in 1D systems, potential energy is just a function of a single parameter, and the force is just a single component. So that force is minus du by dx. These kind of things, so do a bit of revision of it will help in the upcoming chapter. Okay. So now just a couple of minutes I'll take to introduce simple harmonic motion so that we have a smooth ride in the next lecture. So simple harmonic motion is, the term simple here is to signify the fact that it is a straight line motion, okay, or one dimensional. So it is a one dimensional oscillation such that the displacement, okay, from mean position is sinusoidal. That means it's a sine function. Another word for it is harmonic. Harmonic function means sine function. So it is sinusoidal with respect to time. So what this literally means is that if we draw a graph of displacement from the mean position as a function of time, let's say x is equal to displacement, that is one in one dimension, with respect to the mean position, then the graph of x versus time should be shaped like a sine curve. So it's sine curve shaped periodic graph. This is literally the meaning of the term simple harmonic motion. The term simple is to do with the fact that it's one dimensional, and harmonic is to do with that the shape of the graph or the relationship between x and t is a sinusoidal relationship or a harmonic relation. So from that, we understand that the general equation of SHM becomes that x is equal to some constant which is called amplitude into a sine function. Now sine cannot operate on time directly because time has dimension of capital T. So here capital A, omega and phi, these are all constants. And x is the displacement from mean position. T is time. So you can see that dimensionally x has the same dimension as capital A, which is length. Okay. So capital A is expressed in meters or centimeters or millimeters or whatever. And dimensionally you can see that omega t has to have the same dimension as that constant phi, which has to be dimensionless. So that means that omega has the dimension of time inverse. So omega is expressed in radians per second or radians per millisecond or whatever. Okay. Whereas the phase constant phi is expressed in radians. So these are the units in which all these three constants, A, omega, and phi. So this symbol, it looks like W, but it is a Greek symbol, omega. So now we can also see that the moment we write this equation, since sine theta has a range of -1 to 1 for all real values of theta. So therefore, sine of omega t plus phi has a value between +1 and -1, inclusive of both, for all t. So that means x ranges between -a to +a. So that means the maximum magnitude of x is capital A, which is why capital A is called the amplitude. That is the maximum displacement from the mean position. So now capital A has a specific definition that it's the maximum displacement from the mean position, and it's called amplitude.
Sir, can you scroll up a little?
Sure. Okay, it's clear now.
Yes, sir.
Yes.
Yes.
And now just the final thing, the significance of omega. Okay. So we know that sine of theta plus 2n pi in general is equal to sine theta, where n is plus minus 1 plus minus 2, can be 0 also for that matter. So we say that 2 pi is the fundamental period of sine theta. So it is the smallest interval in which the graph repeats itself for sine theta. So likewise, sine of omega t plus phi should be equal to sine of omega into t plus n times capital T plus phi, where capital T is the time period of the SHM, or time period of oscillation basically. So it's, you can also think of it like a fundamental time period. So it's the shortest time in which the motion repeats itself. Okay. So if you compare these two equations, now you can see that omega into nt should be equal to 2n pi, or omega into t should be equal to 2 pi, because this is the fundamental time period of the motion. And because this is, the motion is described by a sine function, so on this side 2 pi is the fundamental period of the sine function. Of the harmonic function. So that is now the significance of omega. So you can see that omega is 2 pi upon time period, or time period is equal to 2 pi by omega. And another term we define as frequency, which is number of cycles per second. That is nothing but 1 by time period. So frequency is omega by 2 pi. So omega, the constant omega is related to the time period of the simple harmonic motion, or the frequency of the simple harmonic motion. Whereas capital A, the amplitude, is all about the range of motion, that is the maximum displacement from mean position. So that is why omega, because it is 2 pi multiplied by frequency, so omega is called the angular frequency. So that is the name of the term, omega. The larger the value of omega, the more frequent the oscillation is, the more the number of cycles per second. Okay, and finally the constant phi, it is called the initial phase, or the phase constant, because at time t equal to 0, the value of x is a sine phi. So phi determines the starting point of the oscillation. For example, if phi is equal to 0, That means x naught is equal to 0. So it starts from the mean position. But if phi is equal to pi by 2, then x naught is equal to plus a. So it starts from the positive x2. Okay. And like that, we'll see more general cases next time. So this is like just the introductory basics into simple harmonic motion and understanding all the terms in the general equation of SHM. So we'll carry it forward from this point onwards next time. So finish your test on Sunday, and after that, if you have some time, maybe you can go through the theory section from Resnick Halliday for the basics of simple harmonic motion, or if you don't have that much time, you can at least do a quick run through of the theory in HC Verma. It will help us in the part coming up. So it's going to be quite conceptual, as well as when we look at applications of various systems that do SHM, then that will cover a lot of concepts from mechanics. There will be systems where we use simple free body diagrams, spring forces, etc. There'll be more complicated systems where we look at rotation. So there'll be torque. There might be application of rolling. There might be application of center of mass, momentum conservation. So literally any and everything that you learned in mechanics can be incorporated into an oscillating system in SHM. So that way it's a very good chapter to revise general mechanics also. So that's it for today's session, people. Wish you all the best, and especially for the test coming up. Thanks for attending. Have a nice day.